Today we wanted to go back to a calculus topic. I got distracted for a couple of days by algebra and arithmetic and such. So today we need to get back to related rates. This is going to be applying the chain rule. The chain rule says dy dx is dy du times du dx. That's just the notation we use for the chain rule. But what we see here are three derivatives. One derivative is the product of these two other derivatives. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. So our setup is going to be a spectator trying to film a car as it drives by. It wants to keep the car in frame as the car drives by at a constant 88 feet per second. Now, even though the car is moving at a constant 88 feet per second, the camera is going to have to spin faster when the car is close. When the car is far away, won't have to spin the camera very fast, but when the car is getting close, we're going to have to spin the camera fast to keep the car in frame. All right. So to that end, we need to define some things. One of the rates of change that we have is the car speeding along this direction at 88 feet per second. Also, the other thing we have here is a triangle where we have one of the angles of the triangle. And we have one of the sides of the triangle. So I'm just going to label another side and bring in a trig function. So here we have a little right triangle. We're going to be interested in how fast the camera is spinning, how theta is changing with respect to time. We have the car moving along this path at a constant 88 feet per second. So it makes sense that this is the leg that we use. We could also see how this length is changing, the distance from the spectator to the car. But we don't have a value for that. All right. So I'm going to say that the car is x feet from the point closest to the spectator, 3 feet to the spectator. The reason I want to use that is because I have information about the car approach, how x is changing with respect to time. So I have information about how x is changing. The 3 feet is constant. This hypotenuse is also changing, but I don't know how. I don't have any information about how that hypotenuse is changing. So I'm going to label x feet from the car to the point on the road closest to the spectator. Once I labeled that distance as x, I can give a name to my 88 feet per second. I can say that the rate of change of x with respect to time is 88 feet per second. Note that I said dx dt is negative 88 feet per second. Why did I call dx dt negative 88 feet per second? Because x is getting smaller. That distance x is decreasing, so our derivative should be negative. So here's how we might ask the question. How fast is theta rotating when the car is 4 feet, when x is 4 feet? Let's think about how fast the camera must rotate in degrees per second when the car at various points along the car's path. Let's say when the car is 40 feet. So we're going to try to calculate how fast the camera has to rotate to keep up with the car at various points along the path. We're expecting it to be a very high number, the highest number when X is 0 feet. So that's when the car is right in front. That's when we're going to have to spin the camera fastest. It should be slower when the car is 40 feet away. So when I ask the question, how fast must the camera rotate? We're asking about a rate of change. How fast is theta changing with respect to time? I also said I wanted it to be changing in degrees per second. That tells you right there what kind of rate we're looking for. Theta being measured in degrees, time being measured in seconds. Said we're asking what is d theta dt? That is, we're trying to find d theta dt. I know that dx dt is negative 88, and I want to calculate d theta dt. Any questions? I need a relationship between x and theta. What's a relationship between x and theta? So here's theta. This line from the distance from the spectator to the car, that's the hypotenuse. That's not something that we know much about. What is x relative to theta? So this is opposite. And what is 3 relative to theta? Adjacent. Yeah, we'll use tangent to get a relationship between x and theta. Tangent of theta is equal to x over 3. I want to solve this equation for, I want to write one of these quantities as a function of the other. So I'm going to solve for x. I'm going to say x is equal to 3 tangent theta. What is the derivative of x with respect to theta? So if I write x equals 3 tangent theta, what is dx d theta? I'll do the hard part. There's a 3 as a coefficient. What's the derivative of tangent of theta with respect to theta? Secant squared. So I've got dx d theta we're looking for d theta dt, and we have dx dt. So we'll notice that the chain rule says that dx dt is dx d theta times d theta dt. We have the dx d theta. Sorry, we have the dx dt. We have an equation for, or a function for dx d theta, and we're looking for d theta dt. So out of the three related rates, we know two of them, which means we can solve for the third one. Any questions? It's just a 2 out of 3 problem. There's three things, three related rates. We know two of them, so we can calculate, we can just divide to find the third one. The dx dt is a constant -88. Dx d theta is 3 secant squared theta. We just have to plug in our various values of x to figure out what theta is, and then find the secant of that. I should have picked a multiple of 3 for our constant speed, but I didn't think it was safe to go over 60. I could have just been under 60. I should have made it 87, because I knew I was putting the spectator 3 feet away. Dang it. Yeah, we're in there now. It's 88. Any questions? Let's make some additional calculations. Funny thing is, we actually don't need to know what theta is. We can figure out what theta is, but we don't need to know that. We need to know the secant of theta so that we can square it. So when x is 40, we could solve for theta, but we don't really need it. So actually, we don't need theta, we need secant of theta. Secant is 1 over cosine, so it's hypotenuse over adjacent. So I just need to know the hypotenuse when x is 40 and adjacent is 3. I just need to know the hypotenuse. So if I make x 40, then the hypotenuse is 3 squared plus 40 squared. Four squared is 16 with 2 zeros plus 9. So square root of 1609. So the secant of theta is hypotenuse over adjacent. We could use this to figure out what theta is, but we actually don't care what theta is. We just care about the secant of theta because we're trying to calculate d theta dt. Which is going to be negative 88 over 3 secant squared theta. So one of the threes cancel. The second 3 gets moved on the top, so I get negative 88 times 3 divided by square root of 1609 square root of 1609. Because there's 2 in the denominator of the denominator. One of them cancels, so the other one's up on top. So I get 0.164 negative. Any questions? Let's see what happens when the car is closer. So when x is 4, still we need secant, not theta. So we'll calculate the hypotenuse, which will be the square root of 3 squared and 4 squared. So the square root of 25 or 5. So the secant of theta is hypotenuse over adjacent 5/3. So now we can calculate d theta dt. So we can see that the camera has to spin much faster. When the car is 40 feet away, we're only the angle is only decreasing. By 0.16 radians per second. But now that the car is this much closer, the camera is spinning much faster. When the car is 3 feet away. Oh. Hold on a second. If x equals 0, we no longer have this triangle. Yeah, all we've got is the car's like right in front of the camera. And how are we supposed to build the triangle? Yeah. What happens? X is 0. Hypotenuse is 3. But also adjacent is 3. So I don't know. What's the secant of 0? Now, what's the secant of 0 is 1 over cosine of 0, and what's cosine of 0? 1. Ah, that's good. It's not one of the undefined parts. So secant of 0 is 1 over cosine of 0. Cosine of 0 is 1, so secant of 0 is also 1. Secant is 1 over cosine. Questions? So we can see what's happening here. As expected, when the car is far away, the camera does not have to rotate very fast. But as the car gets closer, the camera has to increase its rotation. How's everybody okay? The tricky part is going to be this part right here, because that's the part that's not going to be handed to you. Normally, your game in calculus 1 is to take the function that you're given, find the derivative, and maybe set it equal to 0. It probably says optimize or maximize or minimize. You see that stuff, but you're handed a function and you're told to find the derivative. The tricky part here is that you're not going to be given a function. You're going to have to figure out what the relationship is between the two variables. The reason that I do this one is because you definitely don't have the function. It could be, as another example, let's suppose that we have a spherical balloon and that we're putting air into the balloon. Now, as the balloon inflates, the sphere gets larger. As the sphere gets larger, the radius of the sphere is getting larger. So let's suppose we're putting air into the balloon at a constant rate. We want to know at various times how fast is the radius increasing. So we have a constant dv dt, and the question is, what's dr dt? The thing that we weren't given in that entire setup is how are v and r related? How are v and r related in a sphere? What's the formula for the volume of a sphere? No, that's the area of a circle. No, that's a cylinder. 4/3 pi r cubed. It's got to be cubed because the radius is meters, and I need 3 of them to make a meters cubed. Radius, I need an x, a y, and a z. Got 3 dimensions. So I need a radius, and another radius. 4/3 pi r cubed. Remember the coefficient. Yes, the formula for the volume of a sphere. We integrated the surface area. That's also me just talking in circles. That's just the way it works. We couldn't have gotten away with a 2/3 tau r cubed, but we decided to go with pi. I don't know. Maybe I've made fun of the ancient Greeks too much. Pi was a terrible choice. I wasn't at that meeting. I'm like, oh, dude, let's not make pi this important number, the ratio of the circumference to the diameter, but let's make it the circumference to the radius. That's much more important in defining the circle. That's like how we define the circle. It's everything that's the same distance from one point. That's the radius. Now I go, no. We're going to say the ratio to the diameter. I'm like, oh, you guys are going to pay for this in trigonometry. And they're like, oh, what's trigonometry? I'm like, well, that's right. Y'all are going to be dead by the time trigonometry gets invented or discovered, however you want to look at it. And so you won't care. So these poor decisions from thousands of years ago mean we're stuck with friggin' pi. Maybe they were seeing into the future and they said, but if we do tau at 6.28, that's in the middle of summer and teachers won't be able to have pi day. So maybe that's the reason. I don't know. These are just the consequences of arbitrary choices. Also, is pi day the same thing? Do they have pi day like in Europe? Because here it's like 3/14, so March 14. But is it going to be like the 3rd of the 14th month? Wait, no. The 31st of the 4th? No, that's not where the decimal point is. Yeah, I guess they just go with that. I don't know. Also, some people like celebrate pi like down to the minutes, but they still do it at 1 o'clock in the afternoon. 3.14159. 159 is not 159. It's not like right before 2 o'clock in the afternoon. That's right before 2 o'clock in the morning. You shouldn't be celebrating Pi Day at school at all. You should be celebrating Pi Day right before a bar closes. It's like 1:59 in the morning. Yeah, bars close today. All right. So this is the idea behind related rates. We're just going to find some more functions and then take the derivative with respect to some other variable. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing.